So this brings up what is called the trace determinant plane.
Man, what I needed queued up on the soundboard was that Robin Sparkle song about "Let's Go Out to the Mall." That would have been nice. Okay.
So in the trace determinant plane, here's the idea. The type of phase portrait for our linear autonomous planar systems is determined by the eigenvalues, what is often also called spectrum, of the coefficient matrix.
So I'll mention this term here, spectrum, for those that might see more linear algebra in their further or future curriculum. Eigenvalues of a matrix, when gathered together, are often called the spectrum. And so what we're seeing from these diagrams is that if I don't really care about the positioning of the eigenlines, I just need to know whether or not they're sinks and sources, or I need to know whether spirals are happening. I didn't really need to do the full problem. I just needed to know the eigenvalues, because real different, one positive, one negative, saddle, real different, both negative, sink, real different, both positive, source, and then we have the degeneracies, and then we have complex cases as well. And so they all have names, and those names relate back to the eigenvalues.
Okay, so if we just want to study the system, not in fine detail, just an idea, a mugshot of what's going on here, then we just need to consult the eigenvalues. But recall that the determinant of that coefficient matrix A minus lambda I, where A is equal to little a, little b, little c, little d, is equal to lambda squared minus the trace of lambda plus the determinant, and I set that equal to 0, but what is the trace? The trace, we've said, is the sum of the diagonal elements, so that's going to be a plus d, and then the d, the capital D, is the determinant of the A matrix, which I'll write as det A. And what is that going to be? That's going to be, of course, upper left times lower right minus lower left times upper right.
So AD minus BC. So our coefficient matrix would have four things in it, but it turns out because of the patterns that are inside this determinant calculation, what we have then boils down into really two things: the matrix trace and the matrix determinant. And that gobbles up the little a, the little b, the little c, and the little d. So at the end of the day, my eigenvalue equation only depends on capital D and capital
T, which then means if I want to solve for the eigenvalues, lambda plus and lambda minus,
right? This is how I'm going to notate my eigenvalues. There are two of them. They depend on that plus minus
symbol in the quadratic equation. It is going to be negative, negative trace, plus or minus the square root of negative trace quantity squared minus 4 times d all over 2 times a, which is 1. So I get t plus or minus the square root of trace squared minus 4 times determinant all over 2.
Yeah, Kevin's totally on it there. Now, what's going to dictate the type of eigenvalues I get?
Well, the type of eigenvalues I get are going to totally be dictated by what's going on
under this radical, right? So the trace and the determinant appear under the radical, and if that radicand, it's called, goes positive, I'm going to get real roots. If it's 0, I'm going to get repeated roots, and if it goes negative, I'm going to get complex roots. So I should be able to analyze the type of eigenvalues I get based on what's going on with this radicand, or the discriminant it's called, and then maybe what's going on with some other stuff.
So that is the key point. Key point is that the trace, which goes by a couple different names. Your book, I'm going to use capital T because it's just easier, but your book and WebAssign and all that jazz, it's going to use tau,
the Greek letter for T,
and determinant. And I'm going to use D for that because that's easier. But your book is going to use delta, determine the type of eigenvalue. And then what does that mean? Well, the type of eigenvalue then determines the phase diagram is determined by the eigenvalues, right? So
there we go. That's the connection. I boiled it down into this fairly simple formula, which then tells me about the eigenvalues, which then tells me about the phase diagrams. And if I'm not being asked to go into gross detail of exactly where are those eigenlines positioned, then I don't need to, and I can just consult this formula to get the idea. Okay.
So, starting point.
If the discriminant's going to tell us what's going on, then maybe I should think about the simplest thing that I can do to that discriminant, and I'm going to set that discriminant equal to 0.
So let's set that discriminant equal to 0 to just start talking about repeated roots. So if I'm going to start talking about repeated roots, what am I going to say? I'm going to say that t squared minus 4 times d is equal to 0 because that is the discriminant of
my quadratic equation.
Why would I want to study this first? Well,
I like using equal signs, right? I don't want to use inequalities, so I should start with doing equal signs. So I'm going to set this discriminant equal to 0,
and then I am going to solve for capital D.
When I solve for the
determinant will be a function of the trace.
There are only 2 parameters in this game, trace and determinant.
So if I solve for the determinant in terms of trace, what am I going to get? I'm going to get t squared over 4. Okay? So now, and I got to use different axis colors here because I don't want us to get confused with the phase plane drawings that we've done. I'm going to set up this two-dimensional set here, and on the horizontal axis I'm going to have trace, and on the vertical axis I'm going to have determinant, because what I want to do is think about this relationship, determinant being equal to t squared over 4, which is related to my repeated roots. I want to think about this relationship as a function, the determinant being a function of the trace. They're related. If I pick a trace, I'll get a determinant. And if I think about this now in the trace determinant plane, that's what we're drawing here. This is the trace determinant plane. And so I'm going to harp on this just a little bit more. This is the trace determinant plane. Every point in this plane corresponds to some matrix that has this specific trace and this specific determinant where my cursor is. Okay? This is not a phase plane. Every point on this trace determinant plane corresponds to a phase plane. So there are infinitely many phase planes being told to us by this trace determinant plane. And so this is not phase space.
Okay? It is a whole plane of points where every single point in the plane is a corresponding phase space.
Okay.
Yep. But it gives for a good analysis. And where does that analysis start? It starts right here with the determinant being a function of the trace. And in the trace determinant plane, what shape does this make? If D is the vertical axis and T is the horizontal axis and D is equal to T squared over 4, what is that thing? That thing is a parabola. So I'm going to highlight that in orange, and I'll just draw the parabola in here. This is called the repeated root parabola. Yeah. And so what is this parabola trying to say? Well, if your trace and determinant is such that you land directly on this parabola, what do you know? You now know that you're talking about a repeated root. What does it mean to have a repeated root? The repeated root is going to cause this discriminant to go to 0, and if this discriminant is going to go to 0, the only thing that you're going to have left is this eigenvalue, which is the trace divided by 2. So on this repeated root, the eigenvalue, or on this repeated root parabola, the eigenvalue is definitely trace over 2. So, the following question. If you're in quadrant 1 and you're on this orange parabola, you're a repeated root case. So you are some differential equation. If I calculate the eigenvalues are repeated. But if you're in quadrant 1, tell me about the value of your trace. What sort of number is it if you're in quadrant 1 on this orange parabola? Positive or negative? Positive, right? But if trace is positive, tell me about lambda. Lambda is positive. So you know that lambda is repeated and lambda is positive. So what sort of phase diagram would you have if you were a trace and determinant value for your matrix that landed you right here? You would be a degenerate source. Okay, I saw that chat question come up. I'm going to hit it. But hold on, let me write this down. You are a degenerate. I'm not going to write it in orange because I don't think we're going to see the overlay here. So you're going to be a degenerate source. But then if you're on this side of the parabola, your trace has gone negative. If your trace has gone negative, your eigenvalue's gone negative. If your eigenvalue's gone negative and it's repeated, what are you over here? You're a degenerate sink. And so now our goal is to fill out this whole diagram so that I can identify a particular phase portrait with a particular trace and determinant, because that trace and determinant tells me the eigenvalues. Okay? So I'm going to let you meditate on that for a second, and I'm going to check out this chat question. How did we get from t squared minus 4d is equal to 0? Oh yeah, how did we get from here to here? I just solved for determinant. If I solve for determinant, I'm going to move the 4d over to the right, and then I'm going to solve for d, so I'm going to divide by 4. So d is equal to t squared over 4 if t squared minus 4d is 0. What does the d of t mean? Yeah, good question. So what am I talking about here? Thinking f of x. It means that determinant is a function of trace, like f is a function of x, or maybe you want to think of y. Y is a function of x. And now that I'm thinking about determinant being dependent on trace, I'm thinking about drawing a picture in a plane where the dependent variable is determinant and the independent variable is trace. Is a degenerate source the same thing as an unstable source? Well, an unstable source could spiral. It could follow two eigenlines, one at first and then one at the end, or it could follow just one. So it's a very particular type of source. Are all sources unstable? Yes, they are. All right. other questions? So, I mean, we're getting meta here, right? We have these systems. Those systems required required some linear algebra to break down these linear systems. And then we do pictures. And now we're drawing one more picture that characterizes all of those other pictures. So I'm definitely on pause here for a couple more seconds. Let any questions flow in. This is going to be a nice graph. It will help us, and it'll make some future analysis possible, which we're going to do on Monday, and that'll be a wrap. That's the last thing we have to talk about. Cool. Scott's asking, what would the degenerate sink option look like? It would look like this. All right. So, doing a full derivation of the trace determinant plane is not a super great thing to do in this remote environment, because really it works pretty well with making arguments, turning back to the crowd, and then seeing if people are nodding or not nodding. And so what I'm going to do is I'm just going to outline a little bit of it, and then there's a video from summer where I did exactly this, and I'll point you in the direction of that video. But this is what the trace determinant plane will shape up to be in full generality. I'm going to fade out really quick and move the cursor to the outside. This is my repeated root parabola. When trace is positive, these are degenerate sources, so we get one eigenline and trajectories coming out from that eigenline and then bending back around. And then over here on the left-hand side, we have the trace goes negative so that we get this degenerate sink. Again, one eigenline that guides things in, right? And so what we want to do now is we want to talk about the rest of this, but we want to be quick about it, and then we want to start using it. This is going to make more sense if we use it, right? And so I'm going to try to fire up some questions about that in a second, but let's bring out the blue marker here. This will be available in notes. It's also just straight up on the Wikipedia page for anyone that wants to look. If you look up trace determinant plane, this is one of the images that pop up. We're slowly trying to build this out. What I'd like you to do, and I'm going to highlight this in maybe gray. Create little gray boxes here. And then I'm going to ask you to make note that you should look away. Something that we don't talk about a ton in this course is the case when the eigenvalues are 0, and that would correspond to this horizontal line right here. When the eigenvalues are 0, you pick up infinitely many equilibrium points, and you pick up infinitely many equilibrium points because really what you're talking about is a mass spring system with no spring. And so you would throw a particle through space, and there's no spring to try to pull it back to you, and then the particle would just come to rest in the gooey space at some location, and there would be infinitely many locations based on how hard you threw that particle through the goo. But that's not something we talk about a lot, and so we're going to focus on saddle, these sources over here, and these sinks over here. But let's first focus on the saddle. Let me remind everybody that lambda plus minus is equal to t plus or minus the square root of t squared minus 4d all over 2. And that's my formula. I'm going to talk about this saddle in some amount of detail, and then I'll just pay some lip service here to the sources and sinks, and then we're going to move on and try to use this trace determinant formalism. Okay. Notice what this diagram is saying is evidently everything down in quadrant 3, in quadrant 4, they're all saddles. Okay? And this is how the argument works. let's pretend we're in quadrant 4 where my cursor is, and we're looking away from this box here telling me about this horizontal line. I'm down in quadrant 4 proper. If I'm down in quadrant 3 and quadrant 4, what's the determinant always down there? Yep, got to be negative. If you're down in quadrant 3 and quadrant 4, the determinant's negative. So let's look at this. If the determinant's negative, tell me about the number that is negative 4 times determinant. What sort of number is negative 4 times determinant? Yeah, that's going to be positive. Okay? So here's how the arguing is going to work. If you're in quadrant 4, tell me about your trace. I'm in quadrant 4. Tell me about the trace now. What sort of number is it? Positive or negative? Positive, right? So I take this trace, I'm in quadrant 4, which is positive, the trace is positive, and I add on this square root, and since I'm off the repeated root, or since determinant's positive, negative 4 times d is positive, trace squared is positive, so question, is it possible to get an imaginary number out of this discriminant right here, if I'm down in quadrant 4? It is not possible, right? Yep, so I have trace, which is positive, plus the square root of a non-imaginary number. So trace plus that square root is definitely going to be positive. Over here, I'm going to say lambda plus. That's got to be positive. Okay? Now, and this is the tough part in a remote setting because this conversation works a lot better in person. So I'm just going to push us through the conversation here. Check it out. 4 times d. Well, determinant's negative, so negative 4d, that's positive. So trace squared minus 4d, is that number going to be greater than trace squared or less than trace squared when I'm down here in quadrant 4? It's going to be bigger, right? So now I take the square root of a number that's bigger than trace squared. What sort of number am I going to get when I take the square root of a number that's bigger than trace squared? Is it going to be bigger than t or less than t? It's going to be greater than my trace. If I take negative 4d, but d is negative, I take trace squared, I add a little bit to it, I take the square root of that, and what comes out is a little bit bigger, or a lot bigger, than trace. So now I take a positive trace and I subtract some number that's bigger than the trace. What sort of number am I going to get when I do this subtraction? It's going to go negative. Right? And then what happens if one eigenvalue goes positive and one eigenvalue goes negative? Well, I get a saddle. Okay? You perform the same argument over here in quadrant 3, and what you find out is that lambda plus goes negative. Maybe. Hold on. That's negative. I add to that something that's bigger than that. No. I'm just going to leave it. Is lambda plus, I think, goes positive. Lambda minus goes negative. Oh, yeah. Yeah, that makes sense, right? Because trace over here in quadrant 3 is negative. I subtract some square root from it. It becomes more negative. So, yeah, I get a positive eigenvalue and a negative eigenvalue. I get saddles down here. So what have we learned? You look at the coefficient matrix, you calculate its determinant. When you calculate its determinant, you find out that's negative. If you have a negative determinant, where are you? You're in saddle country. It will always be a saddle. Okay? So now, let's think about being up here in quadrant 1. If you're on this repeated root parabola, and you're in quadrant 1, you're a degenerate source. We've just mapped that out. Now tell me, what's going on up here? These are told to me to be sources, but what do I know about being up here? I know that d is greater than t squared over 4. Right? If this parabola is d is equal to t squared over 4, if I'm in this area up here, d must be greater than t squared over 4. But if d is greater than t squared over 4, what do I conclude? That means that 4d is greater than t squared, or that 0, or that, let me write it as
0 must be greater than t squared minus 4d.
But if t squared minus 4d is less than 0, what am I going to get? I'm going to get complex roots. So I'm going to get complex roots if I'm in this area right here. But what do I know about my trace? My trace is positive.
So with positive real part. So I get complex roots with positive real part. What's going on with complex roots with positive real part?
Get a spiral source. Okay. And then if I go down here,
you find out that d must be less than, it's getting crazy. D must be less than t squared over 4. And so that means that 0 must be less than t squared minus 4d, so we get real roots.
And with a little bit more arguing, we would find out that these real roots correspond to a source. So here's the game. If the determinant's negative, you're down in quadrant 3 and quadrant 4, you're a saddle. If you're in quadrant 1 with positive trace and positive determinant, you're a source. I will show you where you can find a video that makes all of the rest of the arguments, and then you'll find out in quadrant 2 you're a sink. Okay, there's one last region that we need to criticize, and that is right here. Tell me, on this line that I'm trying to point out, on the determinant axis, positive determinant axis, what is the trace?
Trace has got to be 0.
And if the trace is 0, this term right here, t over 2 is 0, so I get plus or minus.
So trace is equal to 0 on this line. So lambda plus or minus is equal to plus or minus the square root of negative 4d over 2.
But tell me about the determinant when I'm on this axis right here. What's the determinant? It's a, what sort of number? Positive. But if the determinant's positive, I take the square root of negative 4 times positive determinant. What am I always going to get in that case?
We will always get imaginary. And so if I get only imaginary, this thing's a center.
Okay. So, it is a complicated diagram. What do you want to know about that complicated diagram? You want to know 3 or 4 things. Thing number 1, if determinant is less than 0, you got a saddle. Period.
Part number 2, if the trace is positive and the determinant is positive, you have a source. Part number 3, if the trace is negative and the determinant is positive, you have a sink. Part number 4, if the trace is equal to 0 and the determinant is positive, you've got a center. And then the last thing that I'll say here is there are different types of sources and sinks, right? So how do I figure out which source or sink I'm talking about here? I can look at t squared minus 4d
to figure out whether or not I'm complex, repeated, or real. Okay.